Hello everyone, and welcome to part 2 of the VPL DataGlove series. Over the last week or so, I was able to do a preliminary test of the first method of building a flex sensor from the patent. Here's the first version of that sensor that I built. Let's talk about how this one is supposed to work, then we'll look at how it behaves. This kind of flex sensor has a hollow tube made of some plastic material, and on one end there is a light source such as an LED, and on the other end there is a light sensor such as a photoresistor. When light hits the photoresistor, its resistance decreases, and when the tube bends, less light reaches the sensor. Therefore, as the tube bends, its resistance should increase, which we can detect. As you can see from the video, this is precisely what happened when I did a quick and dirty test of this particular sensor using a multimeter. The behavior is somewhat repeatable and somewhat stable when a bend is held, so having done that initial test, I decided to do more in-depth testing. This particular version of the sensor was made out of a thick, rather stiff plastic, and the dark black produced a very large range of resistance values from as low as a few kiloohms to over 2 megaohms. This multimeter maxes out at 2 megaohms, but another one I have at home read about 8 megaohms at a 90-degree bend, so this is a very large range of values. I wanted to make the tube out of something softer, and hopefully with a smaller range of resistance values, so I replaced that tube with a much softer and more flexible material that I have an abundance of: Ethernet cable jacketing. I had 4 colors on hand, so I made a flex sensor from each, expecting that they would have different optical properties. The amount of bending was measured with a 3D printed tool that the sensor could mount to. I found with the first prototype that one end of the sensor had to be held in place, but the other end has to be allowed to slide. If you don't do this and fix the sensor to both ends, then the material prevents significant bending from happening or becomes detached from the tool. If the material is stretchy, you can stretch the material somewhat, but permanent stretching can occur, which is undesirable. If I had used a foam insert, like in the patent, this might have alleviated the issue, as the tube could be long enough to let the foam take out all of the slack from the bend. But I didn't have any foam on hand, so instead, I let the photoresistor end slide freely. My expectation for the second set of flex sensors was that the colors would impact the baseline resistance, with white being the lowest resistance because it would reflect the most light, while black would absorb the most light and produce very high resistance, and blue and orange would be somewhere in between, with orange maybe having a little less resistance. This turned out to be completely wrong. Here we can see the average measured resistance at 10-degree increments. White had significantly higher resistance overall, while orange had the lowest, slightly below blue and black, which were still much lower than white. I don't have a full explanation for this, but I think some of it is due to leakage. The white tube leaked a significant amount of light, practically glowing, while the blue and orange leaked significantly less. Black didn't leak anything as far as I could tell. So it seems like there's a fine balance between the absorption of different colors and the leakage of different colors or materials. Another interesting thing, which isn't actually visible in the chart, is that the variance in measured values is actually quite high in the white flex sensors, and very low in the orange sensors. The white sensors had readings that could vary by up to 7,000 ohms, with the 90-degree readings being as low as 50 kiloohms and as high as 57 kiloohms. This meant that the white sensors actually had significant overlap between different readings, despite being 10 degrees apart, while the other sensors never had any overlap at all. I only measured a few times, and only measured 10-degree increments, because I don't expect to use these sensors for anything. This proves that they do work, but the problems are enough to make them undesirable. For one, they're very bulky. These tubes are 5 millimeters in diameter, so if they're stiff, that would make gloves very uncomfortable and hard to use. They also have a tendency to experience plastic deformation, and the softer material readily buckles and flattens. That can lead to permanent alteration in the optical behavior, and so any calibration that's been done is ruined. It could even reduce the overall range or precision of the sensor by forcing all the angles to be measured in a compressed low light range. On the other hand, that might actually be desirable, given that the low light regime had the highest changes in proportion to angle, so who knows. Anyway, next time we'll look at the moving optical fiber variation. See you then.